Welcome to YouTube channel scientific underscore math. This is our third lecture on eigenvalues and eigenvectors. And the learning objectives are procedure for finding the eigenvalues and eigenvector. And next we have the example how we can find the eigenvalues and eigenvector. And the third one is the graphical representation of eigenvalues and eigenvector. Okay, so let's start today's lecture. Okay, so this is the third lecture about the eigenvalues and eigenvector. The previous two lectures link is available in video description. You can watch. Okay, so here we discuss the procedure first for finding the eigenvalues and eigenvector. Next we compute the eigenvalues and eigenvector for a given matrix. Okay, so let A be an n cross n square matrix. First we have find the eigenvalues lambda of the given matrix A by solving the equation. That is this one. This is the characteristic equation. Okay. So second step we have for each lambda find the eigenvalues, eigenvector that is non-zero by finding the basic solution to this equation. Okay. So and we also have to verify whether this operation is correct for each lambda and the associated vector or not. Okay, so these steps we have two steps we have to calculate the eigenvalues and the eigenvector. Okay, so we have an example and this in the given matrix of order 2 cross 2 matrix. Okay, so find the eigenvalues and the eigenvector of the given matrix. Solution. First step we have okay find the eigenvalues of the matrix A by solving the characteristics equation. This is the characteristics equation and okay so this the determinant of this one is equal to this one. Okay, so how this comes? Okay, so we can see that determinant of this one lambda into I will be the of same order as the matrix A. 1 0 0 1. Okay, and minus minus 5 minus 7 2 and 4. This is the matrix A. So after simplifying this one we will get this. Okay, so next we have a characteristics equation. This is the shortcut trick for 2 cross 2 matrix to find the eigen. Okay, so this is also the characteristics equation. Characteristic equation for 2 cross 2 matrix. Okay, so how this comes? I will show you how this comes. Okay, for example, we have a 2 cross 2 matrix A11, A12, and A21, A22. Okay, so the determinant of this one minus A, which is equal to lambda into I1001 minus this matrix A11, A21, A2, A12, A21, A22. Okay, so this will be equal to the determinant of lambda 0 0 lambda and minus the matrix A11, A12, A21, and A22. Okay, so this will be equal to determinant of what? Lambda minus A11, A12, A21, and lambda minus A22. Okay, so we multiply this one and with this one. Okay, so we can write this as lambda minus A11 into lambda minus A22 minus A12 and A21. Okay, so again multiply this one with each other. Lambda square minus lambda A22 and minus lambda into A11 and plus A11 and A22. Okay, and minus A12 and A. Okay, so we take common from here, that is lambda A11 and plus A22 rearrange them, plus I can write this one A11, A22, A12, and A21. So we can see that this is the trace of the matrix A. And what is trace sum of diagonal entries? Trace of the matrix A is equal to A11 plus A22. Okay. So and this one is the determinant of the matrix. So I can write it as minus trace of A and plus the determinant of the matrix. Okay. So this is the way this equation characteristics equation comes. Okay. So similarly we can do for the 3 cross 3 matrix, but I will prove also the characteristics equation for 3 cross 3 matrix in next lecture. Okay. So here we can see that the trace of the matrix is equal to trace of the matrix is equal to minus 5 and plus 4, which is equal to minus 1, and the determinant, and we know how to calculate the determinant of this matrix. Okay. So after finding the determinant and the trace of the matrix, then we substitute in this equation. Okay, so after substituting, we have the equation. Okay, this one. So this is the final equation, and now we solve this equation to find out eigenvalue. Okay, so we simplify this equation like that, and after solving, we get the eigenvalues lambda 1, which is equal to 2, and lambda 2 is equal to minus 3. So this means thus there are two eigenspaces or eigenvectors that are one corresponding to each of these eigenvalues. Means we have two eigenvalues, so there will be two eigenvalues against each two eigenvectors against each eigenvalue. Okay, so let's start to find the eigenvectors. By definition, we know that x is equal to lambda 1, x1, x2 is an eigenvector of the matrix A corresponding to an eigenvalue lambda if and only if x is a non-trivial solution to this equation. Non-trivial means non-zero solution to this equation. Okay, so thus that is a okay. So for first we find the eigenvector for lambda 1, that is equal to 2, and we put this 2 in this equation. Now we simplify. Okay, so after simplifying we get this one. Now we write the augmented matrix to this system. We have the augmented matrix reducing into row echelon form. We reduce this augmented matrix into row echelon form. Okay, so after reducing we have this one, and again we write this one as here will be the eigenvector ax is equal to b in this form. Okay, so there will be the matrix, the vector x. Okay, so now multiply. Here we can see that here x is x2 is equal to 0. So we take any arbitrary value, that is the k, and now we multiply this with this one, and after multiplying this we get this, and we simplify and substitute x2 is equal to k. We get x is equal to x1, which is equal to this one. Okay, so we have the eigenvector. This one we take the k common, and now we multiply this with 7 to get the simpler solution to remove the fraction. Okay, so here we have multiplying by this one by 7 to obtain the simpler solution. So we have a simpler solution, this one. Next, this gives the eigenspace or the eigenvector for lambda is equal to lambda 1 is equal to s. So we have this one is the eigenvector corresponding to the lambda 1. Okay, so now we verify our solution. Is that correct or not? To check, we verify that the product of this one will be equal to 2 into the original vector, that is the eigenvector. Okay, so we have this one. This is the matrix A, this is the eigenvector, and after multiplying we get this one, and this is equal to 2 into the original vector, that is the eigenvector. So this is correct. Okay, so the eigenvector is correct. Next, we do similar this for a graphical representation for this uh, eigenvalue and the eigenvector. In this case, the product ax yielded a vector that is 2 times the actual vector. Okay, so we can see that this is 2 times the actual vector, that is eigenvector. Okay, so geometrically multiplication by a has stretched the eigenvector or the vector x by a factor of 2. Okay, so here we have the graphical representation. This is our the original vector x, that is 2 and 7, and after this operation ax, this is equal to 2 times the original vector x. When we multiply the matrix A with the x, we get the vector that is 2 times the original vector, this one. Okay, so there is stretching. Okay, so we can see that this vector is stretched, and this is equal to 2 into 2 and 7. Okay, so this is the graphical representation for uh, lambda 1 and the first eigenvector. Okay, now we do same process for procedure, follow the same procedure for lambda 2, which is equal to -3, and again we solve this equation to find the eigenvector. Okay, so after doing some simplification, we get this one, and we write the augmented matrix for this system, and we have the augmented matrix for this system, this one. And now we reducing into row echelon form, this one. Okay, so we have after uh, mm, uh, reducing into row echelon form, this one. Now in this case we have also free variable, that is x2 is equal to, again we took k, and then we multiply this equation with this one, and x1 minus 1 times x2 is equal to 0, and here we put k is equal to x2, which is equal to k, and we get x1 is equal to k. Okay, so we have the vector, this one we took common for k from this one, it will be this one. So this gives the eigenspace or the eigenvector for lambda 2 is equal to -3 as this one. Okay, this is the eigenvector. Now again we verifying to check. We verified that ax will be equal to the 3 times the original vector xs. Okay, so here we can see that after multiplication, this is the 3 times -3 times the original vector eigenvector, this one x, and this shows the eigenvector is correct. Now we again graphical representation, and in this case this product ax yielded a vector that is 3 times the actual vector, and geometrically multiplication by a has stretched the vector x by a factor of -3, and its orientation means direction or orientational direction has been reversed or opposite to the original vector. Okay, so here we have the uh, vector x, and here we can see this is equal to 1 1, and the new vector after the equation ax, which is equal to -3 times the original vector and -3 times the original vector, and in reverse direction stretched, and in reverse direction are the opposite direction. Okay, so this is for 2 cross 2 matrix. In the next lecture we will solve example of 3 cross 3 matrix, and also we will drive a characteristics equation or the shortcut key to find the eigenvalues of the eigenvector for 3 cross 3 matrix. Okay, so thank you so much for watching my video. Please subscribe my channel scientific underscore math for more videos.